In this video, we're going to practice applying the steady-state open system energy balance. And we're going to apply it on a problem which involves a turbine. I mentioned turbines in previous videos before, but basically they're unit operations that are used to convert essentially kinetic energy into electrical energy. All right? And so on this slide here, I have an example of what a turbine looks like. All right? And I also have a schematic of a turbine as well. Essentially, we have a fluid that enters in at the top. This fluid then spins these blades, and then the fluid exits out the bottom. By causing the blades to spin, it converts its kinetic energy into mechanical energy, and then the torque provided by the spinning of the blades then can be converted into electrical energy as well. All right? So turbines are useful unit operations for converting or creating energy and electricity that we could use. So in this problem statement, what we have going on is we have about 500 kilograms per hour of steam entering into a turbine. The steam enters in at a pressure and inlet temperature and also inlet velocity. The steam then enters in at a point that's about 5 meters below the inlet of the turbine, and it also exits at a different pressure and exit velocity. The turbine delivers a shaft work at a rate of 70 kilowatts, and the heat loss from the turbine is also about 10 to the 4th kilocalories per hour. Based on these process parameters, our goal is to identify and calculate the specific enthalpy change associated with this process. And so based on the information in this problem statement, what I want you to do is to then identify what we could use as a basis and also draw the process flow diagram for this problem statement. Pause the video now and do that. Based on the information in the problem statement, we could draw a process flow diagram that looks like this, where the basis for our problem is 500 kilograms per hour of steam, and we have it entering in at a pressure of 44 atm, temperature of 450 C, and also an inlet velocity of 60 meters per second. In the outlet stream, it's exiting at a pressure of 1 atmosphere and a velocity of 360 meters per second. We're also told that the process itself has a heat loss of 10 to the 4th kilocalories per hour. So since we're losing heat, it's going to be negative there. And also, the turbine is delivering shaft work at a rate of 70 kilowatts. Because the turbine is delivering the work, i.e. the work is going from the steam to its surroundings, our shaft work term here needs to be negative. All right, so that's one thing I want to highlight. All right, also the steam is dropping by a height of about 5 meters, so we're told that Z2 minus Z1 is essentially minus 5 meters there. Now, as far as things we're not told, all right, we're not told what the mass flow rate of the steam is exiting, all right? And the other thing that we want in the end is we want to figure out the enthalpy change in our system, all right? So we want H2 minus H1, which we could abbreviate just as delta H. All right. Okay. All right. So those are the things that we want. All right. So before we could go through and solve this energy balance, what we need to do first is we need to do a degree of freedom analysis in order to make sure we have enough information to solve this problem. All right. And since we're just dealing with mass flow rates, I'm going to do a molecular degree of freedom analysis. And so for this degree of freedom analysis, what we need to count up is our number of unknowns, our number of species, and any other equations that we could use to solve this problem. So at this point, you should pause the video here and you should count up each of these categories and then calculate the degrees of freedom that are available to us. Okay, so at this point, if we count up our number of unknowns, we only have two things in red text. So we have two unknowns, right, which is our exit mass flow rate and our enthalpy change. The number of species we have is just 1, right? It's just the steam. And as far as other equations, we have to remember, now that we're dealing with energy balances, we could always use our energy balance as an additional equation to help us solve for all our variables. All right? So from now on, you should always at least have 1 here at minimum. Okay, so if we count up our degrees of freedom, it should be 2 minus 1 minus 1 gives us 0. And so we can solve for all our unknowns. All right, let's now continue on, and let's apply our material balance to the entire system. All right, so our overall material balance, but we only have 1 species, so it's the same as doing just the steam material balance. So here, let's write our fundamental material balance equation. We could simplify. We're at steady state, so accumulation is equal to 0. And we don't have any reaction going on. So this is also 0. Therefore, we're just left with input minus output. So our input should equal our output vis-a-vis our mass flow rate in should equal our mass flow rate out. All right, so that's easy. We now know what M2 is. It's equal to our basis up here, 500 kilograms per hour of steam. Let's now apply and go through our energy balance. In the previous video, we derived the equation for the energy balance of a steady state open system. And so we could just write that directly here. That's going to be delta H plus E, the kinetic energy, plus the potential energy change. And that's going to be equal to the heat rate and the shaft work rate. For this problem, what we want to calculate is our delta H. All right. So we could rearrange this equation. And just to emphasize, because I may have made it unclear before, that this delta H is going to be equal to our H2 minus H1, which, if I write it in terms of the specific enthalpies, will be this. But we know that the mass flow rates are the same, so we could pull that out. And I'll just write this here. This is M1. So we have M1 is equal to this. In any case, this side is just going to be equal to the heat rate plus the shaft work minus the potential, or the kinetic energy, minus the potential energy change. At this point, we just need to solve for the kinetic and potential energy terms. So for our potential energy, or our kinetic energy, I mean, it's just going to be this. M1 U1 squared over 2. And if I plug in for each of these values, because we know all of these things, at this point it's just plug and chug, we should get a value of 8.75 kilowatts. For the potential energy, we have this. We don't know what Z1 and Z2 are on absolute terms, but fortunately for us, since the mass flow rates are equal to one another, we could factor them out. We could also factor out the gravitational terms, and what we're left with is Z2 minus Z1, which we do know. All right, and so for this one, I'm going to have to do some unit conversion. So what we have for the mass flow rate is 500 kilograms per hour. gravitational acceleration, and then divide that by our gravitational constant term. Multiplied by the difference in the heights. Now we're going to a lower height at the outlet. And now I just need to convert hours to seconds, and this will give us kilowatts if I also divide it by 1,000. In the end, we get a value of negative 6.81 e in negative 3 kilowatts. So I'll highlight here that here it's times 10 to the negative 3. This is much smaller than even the change in the kinetic energy. Alright, so you'll start to see that that change in height of about 5 meters is almost negligible compared to everything else we're going to calculate in this problem. Let's keep going through. And now for the heat term, we're given the heat, but we're given it in kilocalories, so we need to do some unit conversion. So 1 kilojoule is 0.239 kilocalories. Right, and now we need to convert to seconds. And 1 kilowatt is 1 kilojoule. Alright, from here we get that our heat term is negative 11.6. Right, and so once again, this is much larger than the potential energy change. Finally, the shaft work is still just negative 70 kilowatts. So going to the next page, we could go back to our energy balance, and we could calculate what delta H is. Right, by plugging in all these terms. Kilowatts minus 0.75 kilowatts minus negative 6.81 e in negative 3, which almost does not matter at all. Alright, and what we get is we have negative 90, not come out the way I wanted, negative 90.3 kilowatts is equal to our delta H dot. And once again, it's equal to this. And so if we just want to solve for the difference in the specific enthalpies, we just need to divide our delta H dot by that mass flow rate. And what we get is that we have a change of minus 650 kilojoules per kilogram in our turbine system.